Hi everyone. So welcome to IGC classes for HAL examination, right? So this is going to be again the class on analog circuit, right? In few classes we have been talking about op amps and diode and op amp and diode combination. We got to see various question and we solved them right in the class itself, and you got to know how we must approach to any kind of problem. So today, in the last class, I said that I'm going to talk about some non-ideal characteristic of the op amp. Okay, so initially we need to know that what are the ideal characteristic of the op amp, right? So today we will discuss the ideal characteristic of a op amp, right? Ideal characteristics, okay, characteristics of op amp, okay. So what are the ideal characteristic of the op amps? What are the ideal feature of the op amp, you can say, right? So as we know that whenever we say that any op amp is ideal, so we always think about the gain. Okay, so it must have high open loop gain, right? So first of all, the open loop voltage gain, right? Or open loop gain, you can say open loop voltage gain. Okay, what is the meaning of open loop voltage gain? Okay, so it's the any op amp should have infinite voltage gain. Okay, open loop infinite means there should not be any connection between input and output, right? Then only that gain will be known as open loop, right? So open loop voltage gain must be what? Infinite. This is first requirement for the ideal op amp, right? And the second is it is having what? It is having the input impedance infinite, right? So the input impedance of the op amp impedance should be infinite, right? Any op amp this it must have, you know, high input impedance, right? Because the op amp inherently we have like a voltage control voltage source, right? So this is going to be our second requirements for ideal case, right? And the third one is what? The output resistance. What is the meaning of output resistance? Is infinite, sorry, zero or low, you can say, right? Output resistance, output resistance. If somebody is going to ask you that what is the what is the advantage of having zero output resistance in case of op amp, ideal op amp, ideally? Okay, so ideally input impedance of the op amp should be what? Ideally input impedance of the op amp should be zero. Okay, ideally input impedance of the op amp should be zero, right? It means that it can drive any type of load, right? Ideally ideally R out should be what? R out should be zero. Okay, so it can drive, okay, it means that it can drive any kind of load. Okay, any kind of load if the amplifier is having low input output impedance, right? R out, you can say R out. Okay, so sometimes in the examination they will ask what are the ideal characteristic of the op amp. Once upon a time I got to see that in the BARC examination a question was asked, right? So you have to keep this in mind. And if I talk about the bandwidth, if I talk about the bandwidth for the ideal op amp, okay, so the bandwidth for ideal op amp should be infinite, right? Again, infinite. Now you may be thinking that if the op amp is having infinite gain, right, then how can we have the uh, bandwidth infinite, right? So the meaning of bandwidth, the meaning of infinite here is the bandwidth should be high for the ideal op amp. That is, the gain should be constant. Okay, that is, the gain should remain constant over a large range of frequency. Okay, the gain in this case, the gain must be, okay, must be constant over the large range of frequency, okay, over the large range of frequency, okay. Then you will say that the bandwidth is infinite, right, for that ideal op-amp. These things you have to keep in mind, okay. So ideally operating frequency should be from 0 to infinite, right? Ideally operating frequency should be operating frequency should be from 0 to infinity. That's why we must have the high bandwidth for ideal op-amp, high bandwidth, okay. One of the very good parameter, right? Okay. Next is the zero offset voltage. We want zero offset voltage, right? Zero offset, okay. Zero offset voltage. What is the meaning of this? Zero offset voltage. What is the meaning of zero offset voltage? What is the meaning of zero offset voltage, right? So it means that there should be no output if no input is given. Remember, if there is no input to the op-amp, okay, so there should not be any output, right? So that is known as zero offset voltage. It means that you can write here, it means that there should be there should there should be no output, okay, no output if no input is given, no input is given, right, at V1 and V2, okay. So zero offset voltage, zero offset voltage, what is the meaning of that? Zero offset voltage, it means that there should be no output if no input is given at V1 and V2, okay. So there will not be any output, remember this, right? And the next one is the common mode rejection ratio, right? That is known as CMRR, right? Common mode rejection ratio, common mode rejection ratio. Okay, common mode rejection ratio. So the common, ideally op-amp must have the CMRR high. Ideally it must be very high, okay. It must be very high, okay. Ideally it must be very high, right? How the CMRR is defined? CMRR is the ratio of, CMRR, right? CMRR is the ratio of what? CMRR is the ratio of, you can write here, CMRR, okay, CMRR, right? CMRR is the ratio of what? The differential, okay, gain upon the common mode gain, right? ACM. You have to keep this in mind. So in the examination, they will give you differential gain and they will give you common mode gain, right? So if the common mode gain is what? Zero, if the common mode gain is zero, then CMRR will be infinite, right? Okay. So CMRR you have to keep in mind, CMRR, right? So how you can find the common mode gain? Okay, you will have to sort both the terminals, right? You will have to sort both the terminals, okay, minus plus, and then you will find the output, right? So here you will get ACM, okay. So whenever you will sort both the inputs are same and try to find the ACM, right? That is common mode gain. So AD you can here mention AD. What is AD basically? AD is basically the differential mode gain, right? Differential mode gain. Differential mode gain. Okay, today's class is completely related to your HL examinations. I mean, some theory points, right, which you need to keep in mind to brush up those things before you go for the examination, right? So we have done various numericals based on op-amps, and op-amp circuit as well as diode circuit, right? So today we are just focusing on these important points, right? And what is ACM? ACM is the common mode gain, right? ACM is what? The common mode gain. Common mode gain. Okay, right. For CMRR to be infinite, okay, ACM should be 0. If you want, if you want, right, CMRR, right, is infinite, it means that ACM should be what? 0. That is our requirement, okay? Uh, for ideal op amp, right? For non-ideal op amps, the common mode gain will not be 0, so CMRR will not be that high, right? CMRR will be affected. Remember that, okay? It means the effect of noise is not present, okay, at the output. Remember, whenever the common mode gain is 0 here, or CMRR is 0, why we want CMRR to be as high as possible, right? So that the noise will not be present at the output, right? Noise will not, okay, be present at the output. Remember this, right? So these things are very, very important to keep in mind. And the next parameter, which is very, very important, right? Next parameter, which is very important, is the slew rate. Okay, so I'm not going to discuss in detail what is slew rate and all. I mean, how slew rate occurs and all. Just you need to know the formula and the definitions, right? In the regular classroom, we discuss how slew rate occurs, how op-amp goes into slewing, right? How slewing happens, okay? Slew rate is basically a measure of how fast the output voltage change with respect to change in the input voltage, right? Remember, okay? So slew rate is basically what? Slew rate is a measure of, okay? Slew rate is a measure of, sometimes in the examination you will find in the option the definition of slew rate, right? Slew rate is a measure of how fast, okay, how fast the output changes, how fast the output changes with respect to change in the input voltage, with respect to change in, okay, change in the input voltage, right? This is what the slew rate is, okay? So in the examination, definitely this from this concept you will get one question, okay, in the HL examination. Slew rate, right? Slew rate is what? Is a measure of how fast the output changes, output of the op amp, okay, changes, output voltage changes, okay, with respect to change in the input voltage. Ideally the value of slew rate should be infinity, right? Ideally, okay, ideally the value of slew rate, okay, value of slew rate should be infinity again, ideally, right? So in the examination they will ask you the ideal or so you can put infinite, right? Okay, so how mathematically it can be written? So slew rate is equal to what? Rate of change of output, okay, dv naught by dt, right? If dt equal to 0, right, then the slew rate is infinity, okay? You have to keep in mind this, okay? So it is expressed in, you have to keep these things in mind as well. It is expressed, right? Let me erase this. It is expressed in voltage per microsecond. Whenever the values are given for slew rate, if you see the data sheet of analog circuit, Okay, so you will find that the values are given in voltage per microsecond, right? Okay, if there is any small change in input, and okay, so for ideal op amp, output should change instantaneously. The meaning of this, right? If slight, if you are making variation in the input, so your output should change. Okay, there should be the reflection in the output. Understand? This is what the slew rate is. Okay. Okay, so you can also replace this dy by dt with j omega, j 2 pi f, right? J 2 pi f. From here, you can also find the frequency, right? Frequency j omega. Okay, so you can replace it with j 2 pi f, right? So your magnitude of slew rate will be what? The 2 pi f into v naught. Okay, into v naught. Okay, this is what you have to keep this in mind, right? The next one is next important feature of the op amp is power supply rejection ratio, right? Power supply rejection ratio. Okay, power supply rejection ratio. Okay, which is also known as PSRR, right? PSRR, right? So it is a measure of change in the input offset voltage, right? It is a measure of, see why I'm giving you the definition, because sometimes in the examination they will give some definition in the options, right? So you must know what is the meaning of PSRR, right? So power supply rejection ratio means it is a measure of what? It is a measure of change in, right? Change in input offset, change in input offset voltage with, okay, with change in input offset voltage with change in input supply, change in input supply, right? Input supply, okay, supply voltage. So these are the important points. Okay, it is a measure of what? The change in the input offset voltage with the change in the input, with change in input supply voltage, right? Ideally the PSRR should be 0, remember. Okay, ideally PSRR should be 0. This is very, very important. Okay, so your open loop gain should be infinity, your R input should be infinity, your R out should be 0, your bandwidth must be infinite, right? Your CMRR must be infinite, your that offset voltage, right? Offset voltage, the offset should be 0, right? Your PSRR should be 0. So these are very important characteristics, right? You have to keep this in mind. Okay. So these are very, very important things. And practically, if you want to see, so high means it will be of the range 10 raised to power 6, right? It will be in mega ohm, okay? It will be in just milli, or you can say ohm, right? The bandwidth must be finite. What is the meaning of bandwidth? The meaning of bandwidth infinite here is that the gain should be constant over the large range of frequency, understand? And this guy is the ratio of differential gain upon ACM, always given in dB, right? And this offset voltage, if there is no input, okay, so there should not be any output, and this is what the change in the input offset voltage due to change in the power supply, okay, input power supply. These things are very, very important, which you need to keep in mind. right? Okay, this is what I wanted to discuss for today. Okay, so let me take few questions here. Okay, and solve the so already I have told you that the slew rate calculation for slew, what is slew rate basically, right? That is the maximum rate of change of the output voltage with respect to time, you can say. Okay, so let me calculate some, so you can write here the slew rate calculation for op-amp. Slew rate calculation for op-amp. Okay, this is very, very important topic. Okay, everywhere you will find this everywhere you will find the question related to this topic, slew rate calculation, right? So already I have defined that the slew rate is what the rate of change of output voltage with respect to time, that is dv naught by dt, and this is the maximum. Okay, max. Okay, so yes, and it is the capacitance which is the main culprit of decreasing the value of slew rate. Okay, if there will be capacitance, then definitely the slew rate will be decreased, right? So you can write here which element, okay, decrease the slew rate. Okay, remember, so it is the capacitance. Okay, it is the capacitance which is the main culprit, which is the main culprit, right? Which is the main culprit of decreasing value of SR, right? Value of S dot R. Remember, this is the element, right, in the op-amp which will be present. Okay, so what is I here? What is the relation between I and V in case of capacitance? So I equal to basically C dV C by dt. So you have to keep this in mind, right? What is I max here? What is I max? So I max will be equal to C dV naught by dt, right? And dV naught by dt is basically the slew rate. Okay, this guy is the slew rate here, right? Slew rate. So you can say that the slew rate is can also be defined as the I maximum upon the capacitance C, right? Here you can see if the C is increasing, the slew rate will decrease. Okay. So if I talk about the orders, right? So I max uh, is of the order of order of, you can say, 15 microampere, of the order of 15 microampere. Okay, and the captions of the order of, okay, of the order of, these are the approximate value I'm just giving, 30 picofarad, right? Okay, if I max is 15 microampere and capacitance is 30 picofarad, then what is the slew rate value? What will be the slew rate value? Let me make the quick calculation here. The slew rate is equal to what? The slew rate will be equal to 0 0.5, 0 0.5, this is micro and this is pico, right? So you will get here the mega ampere upon farad, right? So you can say that this will be giving you 0 0.5 upon microsecond, right? This will be the value of, okay, so please keep this in mind. Suppose the input is sinusoidal. Okay, suppose any op amp is given. This is just a buffer circuit I'm giving you. Like I said when I was talking about buffer, so I said that we will discuss about you know frequency response of this op amp as well. So now the VI is what? The VI is basically Vm sine omega t. Okay, Vm sine omega t. So what shall be the output here? Output will be same. Okay, the V naught will be equal to Vm sine omega t only. How? Because the Vi is directly connected to V naught. You can see here, this is just a buffer circuit, right? Just a buffer circuit. Okay, this is just a buffer circuit, right? So here you can see Vi is equal to this. So V naught will be equal to Vm sine omega t. Okay, so your output is depending upon the input frequency as well, right? So now we can compute SR, slew rate. Slew rate is equal to what? dV naught by dt. So we can put this guy here, right? We can put this guy here. So what shall be dV naught by dt? You can put here that is dVm sine omega t upon dt. So you can differentiate this, right? So the slew rate maximum is what? The slew rate maximum you will get here is that you will get A. If you differentiate, right? Let me differentiate first. Let me differentiate that Vm sine omega t, right? So what you will get after differentiation? You will get that that is as Vm omega cos omega t, right? Cos omega t. If I try to find the maximum one, so we'll have to put 0 here. So the maximum slew rate, okay, maximum slew rate, you can see maximum slew rate will be Vm, you can say, and omega m. This is the maximum. That is, you can say that 2 pi Fm and the peak of the input signal, right? That is Fm, right? If the gain is 1, this is valid. This is valid for buffer circuit, right? Buffer. If the gain is 1, okay? Otherwise, it is not applicable. Understand? Okay. So you can find the maximum frequency as well. Many times question has been asked from this topic, right? The maximum frequency of the op-amp, okay? Whenever the slew rate is given, okay? So you can determine with the help of this formula, right? So Vm, like this. So omega max is what? Omega max is basically the frequency, okay, calculated by the experiment, okay, with the voltage follower, okay, where the output starts showing distortion with respect to input, remember. So this is of omega, which can be written as 2 pi f max, okay, which is equal to you can say that this is SR max, right? So from here you can compute f max as the slew rate maximum upon 2 pi. Okay, this is important formula which you have to keep this in mind for the HAL examination, right? Okay. So let me take one numerical problem. So question number 1, which has been asked in IES, okay, or you can say in ISRO HAL, okay. So an op-amp has gain of 40 dB, and op-amp has a gain of 40 dB, right? 40 dB, and input signal frequency and input signal frequency, okay, input signal frequency is given as 20k hertz, okay, is given as 20k hertz, right? What is the maximum value of input? Okay, in the question they have asked that what is the maximum value of input, maximum value of input for undistorted output, undistorted output. Okay, slew rate is also given. If slew rate is given as what? It's given as 0.5 volt per microsecond, right? So you have to find the maximum value of the input. What you have to find here? Maximum value of the input, this, for the undistorted output. So this is a question suppose asked in HL examination. So how you're going to solve this, right? So everything is given here. So first of all, you can point, you can write down what are what is the what are the parameter given. The gain is given as what? The gain is given as 40 dB, right? The gain is given as 40 dB, and the frequency f is given as 20 kilohertz, right? And you have to find the maximum, and slew rate is given as 0.5 volt per microsecond, right? So as we know that the formula, that is f max is equal to slew rate max, right, upon 2 pi a f max, sorry, 2 pi, just let me erase this. What was the formula here? Let me get back and check. Yes, yeah. So slew rate maximum was what? Vm sine omega t as Vm omega m, right? So from here we can find out what? We forgot this actually, right? We forgot Vm here. Okay, the maximum amplitude of the input here. Please correct this, okay? And then an op amp has the gain. This is gain is given, right? So what is gain? Basically the output upon input voltage. Okay, that will give you the gain. Okay, so with that you can find easily the maximum value of the input, right? This time the gain is not given as 1. Okay, this time the gain is different, right? Please keep this in mind. So let me raise this as well. Okay, so you have to be slightly cautious while using the formula and all, right? That's why whenever I solve the circuits, I find circuit very easy way of solving instead of solving some these theoretical questions, right? So, so here the Vm can be computed as SR max upon, okay, upon 2 pi f max, right, into the gain A, right? This is how you can compute. So see, initially that formula was valid for when V out was equal to Vi, but now V out upon Vi is given, right? What is given? They have given some gain here, right? That is A. Okay, so please keep this in mind. So from here you can say that the V out is equal to A times of Vi. Okay, and you have to find Vi only. Okay, so please keep this in mind, this formula. This is valid for any, okay, any kind of op-amp, whether it has unity gain or non-unity gain, right? So let me plug the given values. That is Vm is equal to SR max upon 2 pi f max times A. So let me keep here the values, okay, that is 0.5 upon if there is a 10 raised to power something, right? So uh, you have to keep in mind these things, right? The slew rate is what? Slew rate is 0.6 into 0.5 into 10 raised to power 6, because there was micro in denominator, right? Voltage per microsecond. So you can take this 10 raised to power 6 up, and 2 pi into uh, you know 2 pi into this frequency was given as 20, I guess. So 20 into 10 raised to power 3. Okay, and you can find the gain from 40 dB, which is 100 approximately, right? So 100, And if you will compute here, so the Vm you will get here is that Vm, this is very easy problem. So Vm you will get at 0.0398 voltage. So please keep this in mind, okay? Please keep this in mind and correct this slew rate here. We forgot Vm, okay, to keep. So slew rate is very, very important, right? In the exam, they can give you slew rate, okay, and they can ask what is the maximum value of input for undistorted output, right? Op-amp has gain of 40 dB and the input signal is given. Right, this is how we can take more questions, right? So one more question which has been asked in your exams, that is an op-amp has slew rate of an op-amp has slew rate of 100 volt per microsecond for a frequency of 10 megahertz, right? 10 megahertz. The maximum peak value of the sine wave, the maximum peak value, okay, peak value of the sine wave of the sine wave output, right? Output voltage will be. So this kind of question can also be asked. Voltage will be, right? And they will give you some options. So how can you find this? So we know that the maximum frequency is what? Maximum frequency is equal to the SR max upon 2 pi times of Vm, right? Now they did not mention about gain and all, right? So consider the unity, gain, right? Unity gain. Remember, consider the unity gain, okay? Or they might give you 0 dB as well, right? So you have to keep this in mind. So F max is equal to this. So you have to find what? You have to find Vm. Vm is equal to what? Vm equal to SR upon 2 pi F max, right? So here you can plug the values, okay? So SR is what? SR is given as 100 into 10 raised to power 6 upon 2 pi into F max. F max is given as 10 into 10 raised to power 6. So it will get cancelled. This is also cancelled. Okay. And now 10 upon 2 pi. 10 upon 2 pi. What is the value of 10 upon 2 pi? You can solve this, right? So this will give you 1.592, right? 1.592. So this kind of a question can also be asked. Please keep this in mind, right? So today I discussed about these things. So slew rate is very, very important. Slew rate, okay, slew rate. And the calculation of slew rate, this is the ideal requirement for the op-amp, ideal op-amp, okay, for ideal op-amp, this is the requirements. Okay, you have to keep this in mind. And please correct this, we made mistake here, right? Because of next slide, yes. And what is the calculation whenever the input is not sinusoidal, right? Suppose the input is not sinusoidal, okay, non-sinusoidal, then how can you calculate the slew rate? So remember that calculation of slew rate, okay, for non-sinusoidal, okay, so sinusoidal input. Till now we were talking about if the input is sinusoidal, Vm sin omega t, then we were trying to calculate the slew rate. But now suppose Vi is like this. this kind of a waveform, right? This kind of a waveform. So this is Vi. Okay. Then how can you find the slew rate, right? How can you find the slew rate? So let me draw the Vi here. There is a discontinuity, okay, in the input signal. You can see here that is Vi, right? So let me draw the output here. So as far as we know the definition of slew rate, how fast the output changes with respect to the input change, right? So here the changes occur, right, in case of input. Here the changes occur in case of input. So we have to see how fast your output is also changing. Okay, that is the okay. So that is going to give you the slew rate of the circuit, right? So you can see here your input is changing from high to low, right? So you can say that my output is also changing like this, slowly, right? Or it will get settled here. Again it will change, okay, like this. So you can say there is a delta t change in time, right? And there is a change in output voltage, right? Change in output voltage. So the slew rate can be defined as the change in V out upon the change in time. Okay, this is valid for non-sinusoidal, okay, valid for non-sinusoidal input, right? Okay, so these things are also not taught everywhere. Just I'm telling you so that if any question will be given, you can solve this, right? So definition is same, right? You have to find the maximum slope, okay? That is going to be giving you the slope. That is going to be giving you the slew rate, right? How fast your output is changing here, right? Let me take one question as well. Here the question says that an output is any op-amp. If I talk about any question, right, any PSU question, so let me take that question. An op-amp is used as an op-amp is used as zero crossing detector. Zero crossing detector. Okay, op-amp has various applications used as zero crossing detector if maximum output available, if maximum output available, maximum output available from op-amp, maximum output available from op-amp is plus minus 12, right? Plus minus 12 volt peak to peak, peak to peak. And slew rate is 12 volt, okay, per microsecond. Then what is the maximum frequency? Then what is the maximum frequency? What is maximum frequency of input signal, of input signal that can be applied, okay, that can be applied without causing, a reduction in power, peak to peak output voltage, without causing a reduction in, okay, reduction in peak to peak output voltage. See the question how they have designed. An op-amp is used as a zero crossing detector. This is one application of the op-amp where the maximum output available is plus minus 12 volt peak to peak, right? And the slew rate is this. what is the maximum frequency we have to find? Okay, that can be applied without causing the reduction in peak to peak output voltage. Okay, this you have to keep this in mind. Understand? So let me solve this problem. This problem is very good problem. Okay, so as we know that the rate of change of V naught and change in time is defined as the slew rate. Okay, and 1 by delta t is what? 1 by delta t is basically f, right? We know. So f is basically what? F will be equal to slew rate upon change in V naught, right? Change in V naught. Understand? So here the slew rate is given as 12. You can take and change in V naught is also 12, right? We can say that this is 12 as well, and this is 10 raised to power 6. What is the value of frequency? That is 1 megahertz. Okay, so very easy problem. Okay, you can solve this, right? Okay, and we have done various problems. So this is one concept from where question can be expected, right? And so with this, the op amp is over, and diode also we have discussed. We discussed about clipper, clamper, peak detector, right? So let me revise that as well. So we have discussed about clipper, right? So clipper was designed with the help of a simple resistor, plus diode, right? And the way the voltage is measured across which element, that was deciding what kind of clipper is that, right? And in case of clamper, okay, in case of clamper we went for capacitor, right, and the diode, and the output is measured across the diode, right? Output is measured across the diode. These things we have discussed, and if we are measuring the output across the capacitor, that was peak detector, right? So we have discussed about peak detector as well. So question definitely can be asked from these topics, right? Peak detector. So the output is measured across capacitance. Right? Great. So please keep this in mind. Uh, do watch a study class, okay, and you will get everything there. Right. So we were talking about clamper, clipper, peak detector, and so on and so forth. Okay. So let me take few more problems based on uh, which can be asked, in your examinations. Right. Okay. So let me take a few more concept and problems which will be definitely asked in your exam. So with this diode and op amp, I think is we can say is over. But one very important concept from the diode circuit is the small circuit, small signal analysis, right? Small signal analysis of a diode, right? A small signal analysis of diode. Okay, this is very, very important. From there also, from this topic also, you can expect few questions. So this I want to discuss, right? So as far as we know that the semiconductor diode is having semiconductor diode, right? Semiconductor diode is having what? If we apply some voltage, diode voltage, so it allows some current ID, right? And the ID is basically given by I naught e raised to power eta Vt minus 1. So this is what the diode equation is, okay? So as far as we know that suppose IV characteristic, if I draw, this is ID versus VD, right? ID versus VD, we know that it has exponential characteristic like this, okay? In the forward bias, it has exponential characteristic, and in the reverse bias, as we increase the reverse bias voltage, so the current initially is 0 or constant, you can say, and then if you increase enormously, so the current will start flowing huge, right? Remember. So if we apply some signal here, right, any kind of signals, okay, whether it is large or small, right, about this point, right, so what you will get here is that you will get output at 0. You can see output is 0 here, right? So whether signal is small, large, or small, right, you will get 0 voltage, okay, 0 output, right? Okay. And but if you add suppose signal is very big, if you keep the signal small and add DC to it, right, if you add DC to it, okay, because this entire IV characteristic is what the exponential one, right? But if you see this segment closely, right, this segment closely, so it is looking like a linear straight line, okay, linear one, right, linear region. So what you can do here is you can shift this AC waveform, you can shift this input signal by adding some DC, okay, to here, right? How can you shift? Just with the help of clamper circuit, right? With the help of clamper circuit, you can shift this DC AC signal to DC here, right? So your signal will be here, right? And you have to keep the signal small as well, okay? You have to keep the signal small. So now your signal is here, okay? Now your signal is here. Once now you can measure the output here, right? Whatever input you are applying, this is your input and this is your output, right? Whatever input you are applying, you are getting the same output. So what you are doing here is the step of small signal analysis is what? Small signal analysis in general analysis, right? Number one is what? Keep add DC, right? Add DC to AC signal. Okay. Second, keep the signal small. Keep the signal small. Okay. Because after all, you can amplify that signal, right? And third one is what? The moment you do this, right? The moment you do this, your diode becomes a resistance, right? So then you can operate in linear region, right? Okay. That will give you linear picture of the diode, right? Linear picture of diode. Okay. So you can replace, okay, we can replace diode with resistance, right? With resistor. Okay, so your diode journey will start from non-linear and it will become resistance, right? Okay, you have to keep this in mind. Okay, in general, how and what is the value of this R? Okay, we have to find out, right? So what we are doing here is we are suppose let me take one experiment here, right, to explain you. Experiment, just I'm trying to explain you, right? Suppose this is a music, right? Music source is here, and there is a LED, right? You can say LED. LED is also kind of a diode only, right? So if you are what you're doing here is you are giving some here you are playing some music, right? Some music you are playing, okay? Music you're playing, and there is a photo register here, and at this end there is no connection at all, right? And this is a photo register, okay? Photo, okay, photo register, okay, which will accept some photo, or you can say light, and there is a speaker, right? Okay, there is a speaker to listen the music, right? Okay, so now what will happen here is that the moment you will play the music, okay, so here the current will flow, and current is directly proportional to the light intensity, right? Light intensity. Okay, so this light intensity will fall on this photo detector, okay, you can say photo register, and the music should be played here at the receiver, right? You should be able to listen the music, okay, but this LED is basically a non-linear device. LED is what? A non-linear device, okay. LED is non-linear device, okay. So what will happen, you will not be able to recover the music back to your ear. Understand, whatever music you are playing at one end, right, and you want at a at another end, right, you want to listen the music back, okay, whether you increase the volume of this music, okay, the light intensity here, it will fall here, right, and it will here, there should be reflection, right? You should be able to hear the music at this end, right? There is some distance apart, okay, but you are not able to recover the music. Why? There is no music, right? No music, or you can say there will be distortion in music. You will not be able to identify which song is being played, okay, at the source side, okay. What is the reason behind that? Because of non-linear device. LED is a non-linear device, right? Okay, so LED is a non-linear device, okay, and it has this characteristic like this, okay, it has the characteristic like this, and you are playing the music here, be it having like this, okay, the music is being played here, right? So and you're trying to listen back, so you can't listen back, okay, you can't listen it. See, there is a distortion, you are getting zero, okay. But what you can do here is, as far as your LED is a non-linear device, as far as LED is what? Non-linear device, you can convert LED to linear device. How you can convert? How you can convert non-linear device to linear device? Okay, this is my question. How we can convert non-linear device to linear device? Answer what? What is the answer? With the help of small signal analysis. With the help of small signal analysis, right? Okay, this is very, very important. Okay, nobody knows what is small signal analysis, right? So this is in general the concept, right? So once you go for what you have to do, then number one you have to do is, there are three steps, right? Add DC to AC, add DC to music, right, you can say, and keep the keep the signal small, right? Keep the volume of a music at very low stereo, you can say, keep the signal small, okay, and then convert, diode journey will be from non-linear to the resistance. Now the question is, what is the value of this R AC, you can see, okay, understand. DC is added just to get what, just to clamp up your AC signal, that's it. Okay. So whenever you will go for AC analysis, uh, so what you will have to do, you will have to replace diode with the you will have to replace diode with resistor, right? In case of AC analysis, okay, then you will go for AC analysis. But the resistor value will be depending upon the current, diode current, which can be found out with the help of DC analysis. So DC analysis will be done to calculate the current so that you could get the resistor, right? So let me explain you mathematically, okay, mathematically how you can get the value of AC resistance, right? So we have to do what, this is ID, right? ID. So here we can add, DC, you can say AC, ID AC plus ID DC, right? Equal to what? I naught e raised to power, VD DC plus VD AC, right? Upon eta Vt, right? You can neglect one, okay, for the time being. So what we are doing here is, this is AC signal, and this is though AC signal, the I should be small, okay, because we are saying that we need to keep the signal small, but at present you have to focus here that this is overall AC quantity only, no matter it is capital, written in capital letter, right? Because in the sub you can see there I have written the AC. So it is AC quantity, and this is DC. So what we are doing here is we are doing AC plus DC for current. So there should be AC plus DC in the voltage, diode voltage as well, right? So e raised to power m plus n means e raised to power m plus e raised to power n. So you can divide this, okay, you can write separately here, right? So what will happen here is that ID AC plus ID DC equal to I naught, right, e raised to power VD AC by eta VT, okay, eta VT e raised to power this can be written as VD DC by eta VT, okay, and this is okay, right? Okay. So what we can do here is, you can, as far as this VD AC, this is very small, right? This is very small. Okay, this we have to compare we have to consider very small compared to VT, right? Here VD, if VD is VD AC is very small compared to VT. Okay, VT is what? 25 millivolt at the rate 300K, right? That is thermal voltage, as I told in the study class. So what you can do here is you can approximate this. So e raised to power x can be written as 1 plus x. Okay, this can be written as 1 plus x, right? So here I naught e raised to power, let me erase this again. Right, so I naught, this can be written as 1 plus VD AC, right? VD AC upon eta VT, okay, in the bracket, okay, and then it should be written, right? Okay. So what is this basically? What is this basically, right? What is this? This is basically ID, right? I mean, once you will multiply this, so you can say that is ID only, okay? That is ID. And we are neglecting what? We are neglecting one, so you can neglect this one as well. So what will happen here is that, or else you can just keep this as it is. So let me erase this I, okay, unless you get this I naught times this, then only you can say this is ID. So keep this as it is, e raised to power VD DC by VT, right? Now what will happen is that Further, you can, this is IDAC plus IDDC. Okay, so you have to see, you have to only focus on the result. Okay, what is the value of resistance? That is our main objective. So I naught e raised to power, I naught e raised to power what? VDDC, okay, upon eta VT plus I naught e raised to power VDDC upon eta VT dot VDAC by eta VT, right? That is the factor which we have got. Okay. Now you can see here, this guy is your ID DC. This and this gets cancelled. Okay, and this is ID only. ID DC. DC. Okay, from DC picture you will get this diode current. Okay. Now what we can say here is that IDAC, diode current of the AC equivalent, right? Plus, sorry, not plus here. Now it has been cancelled, right? So what will happen here is that this is equal to ID DC into VDAC by eta VT, right? Now you can take the ratio of VDAC upon IDAC, right? VDAC upon IDAC, VDAC upon ID, VDAC upon that, right? So what will happen is that eta VT by IDDC, right? Okay, this is the resistance RAC. Okay, this is the value of resistance where eta can be 1 or 2, right, for silicon and germanium, and you have to focus on. Okay, so this guy can be computed with by DC analysis. Okay, and this will given 25 millivolt at the rate 300k, right? 25 volt at the rate 300k, right? Okay, so I hope you understood how to calculate or how to compute 25 millivolt at the rate 300k, right? How to compute this RAC. Okay, so nothing to worry about. If you know the approximation, you can do. Why we are approximating e raised to power x equal to 1 plus x? Because we are neglecting higher order term of this Taylor series, right? Basically this is the Taylor series, right? Taylor series, and we are neglecting higher order term because the voltage across the diode is pretty small, okay, compared to the thermal voltage, right? So please keep this in mind. Okay, this is very, very important, and I have told you experiments as well. So now you can happily convert nonlinear device to linear device. So your diode will be present here, and its equivalent, AC equivalent is what? The eta VT by ID. ID is what? The DC current of the diode, right? Okay. So this is what the small signal analysis of a diode, right? You have to keep this in mind. Now I would like to talk about few more, I would like to take some problem, okay, from gate examinations, so that right. So I will take one problem from gate 2022. Okay. One problem was from small signal analysis of a diode only. So we will see, right? Okay. So this problem was asked in gate 2022. Okay. So this, see how what kind of problem they are giving, and how you have to approach basically, okay, if you know the concept. So GATE 2022 EC paper, right? Along with the IV characteristic, they gave question. So how basically I'm gonna approach. So you have to learn that, okay? How basically I'm going to approach, you have to learn that. You will be able to solve these kind of questions very, very easily, right? Okay. So let me write the question here so that you will understand everything. A circuit and the characteristic of a diode is given, right? A circuit and the characteristic of the diode are shown, right? So circuit is given and the IV characteristic is given, right? The ratio of minimum to maximum small signal voltage gain. The ratio of minimum to the maximum. Ratio of minimum to maximum small signal voltage gain that is dV out on dV in is, okay. They have asked this question. This was the question asked in GATE 2022 EC paper, right? So this kind of question can be expected also in the HCL examination. So the circuit and the characteristic of a diode are shown, and the ratio you have to find of the minimum to the maximum small signal voltage gain dV out upon dou V in. Let me draw the circuit here. Circuit is very basic circuit. There is a resistance, okay, and there is a resistance and there is a resistance, right? In the IV characteristic, they did not give you any slope, kind of finite slope, right? So in the IV, there is a infinite slope, okay? The diode is ideal only, but they have given the along with the cutting voltage, right? So this kind of a IV is given 0.7, and this is voltage V and this is I, and the diode is given here plus minus V and the current is I. This is what the picture given, okay? And the values they have given is 2K, this is 2K, this is 2K, right? This is 2K, 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 and very good problem this was framed, right? So in if somebody knows the concept which I discussed yesterday and today, okay, they can use, right? So how fast I can solve this problem, right? So the V max and V min, okay, V max and V min we have to find, right? So okay, when the diode is on, right? When diode will be on, when diode will be on, when diode will be on, so this diode will be replaced by short circuited, right? Because the slope is what? Slope here is, slope here is what? Slope here is infinite, right? Infinite. It means that the resistance equal to 1 upon slope, that is equal to 0. So diode will be replaced by short circuited, okay, when the diode will be on. When diode is going to be on? When V in is greater than 0.7, right? Okay. When diode will be on? When diode will be on? When diode is input is greater than 0.7, okay, then diode will be on. and once the diode is on, it is short circuited, then this 2k will be what? This 2k will be gone, right? And when, so there are two cases, right? The case number one is what? When the input is less than 0.7, right? Or you can say diode voltage across the diode 0.7, right? So diode is off, right? You can say. So diode can be replaced by open circuited. Okay, so you can compute, you can draw the circuit here now. This kind of a circuit you will get. Okay, so this is V in. Okay, this is V in, and plus minus. So you have to compute the voltage here, that is V out, and this is 2k, this is 2k, and this is 2k, right? So you can compute the gain now. So how can you compute the gain? You can say that uh, this is 4k. Okay, so you have to find the voltage, total voltage across 4k, and all voltage are in series, so you can apply voltage division. By voltage division, right? By voltage division. Okay, by voltage division, you can say that V out is equal to 4 into V in upon total, that is 6. So you can say this will be 2 by 3 V in. Okay, this is 2 by 3 V in you have got. So from here you can compute V out upon V in, that is 2 by 3. Okay, this is the small signal gain only, right? Small signal gain. Now because the signal is pretty small, again what you can do, second case is what? When V in is greater than 0.7, right? So your diode will turn on, your diode would be on, and your this resistance, and there is a resistance, right? So your diode is on. So now this time this will be short circuited, this 2k, this 2k, and this 2k, plus minus. Okay, so this is how you can solve the problem. This problem was very easy, right, in gate exam. So voltage across the diode, remember initially when the diode is off, you can say 0.7 is not there, or diode voltage across the diode, you can say VD is greater than 0.7, or you can say here the VD is less than 0.7, the diode will be off. Okay, like that you can say. So now if this is short, this will be short, right? So you can make it short, right? Now V out equal to what? Will be V in by 2, because both resistance are same, so voltage division. So from here V out upon V in will be 1 by 2, right? So this is what? This is basically 0.66 and this is 0.5, right? So maximum is this and minimum is this. What was the question here? The question was the minimum to maximum, right? So the minimum is what? The minimum is minimum upon max is what? Minimum is 0.5 and the maximum is 0.66, or you can say 1 by 2 upon 2 by 3. 1 by 2 upon, let me write here, 1 by 2 upon 2 by 3, right? Or you can say that 3 by 4, which gives you 0.75. So answer was for this question 0.75. Okay, so this is how we can solve the question, right? See, there was no formula and all, only IV characteristic is given, right? And with the help of these slopes, already we have discussed how can you find the resistance from the slope. Okay, and everything can be computed, right? So the V max is 2 by 3 and the V min is the minimum small signal voltage you can consider is 0.5 and you can get the answer. Okay, right. So this was a problem, very good problem they had asked, and you have to take care of this, right? Okay, so let me take more problems, right? And so that you will, and from the next session, we will start new topic, bipolar junction transistor and MOSFET. So we will solve more problem from them as well. And we will also cover oscillators and Smith triggers. Okay, because questions can be expected from those topics as well, right? Right. So let me take one more problem from GATE 2021. EC paper only. So GATE 2021. EC paper, right? So let me take very good problem, right? So as far as we discuss about clipper, clamper, okay, and small signal analysis of a diode. So once you will practice many questions only from previous year, whether you can take GATE 2021 or ESE paper, okay, or ESE paper, or you can say the ISRO papers, right? So you will get very good problems, right? So you will be able to have the practice. Uh, okay. I have already discussed one of the very good problem from the op-amp when the when they asked that this kind of a problem we discussed, it was asked in you know in GATE 2021 only. So this was the problem. It was having the capacitance here, right? Already we have discussed this problem, I think. Okay, and they asked the voltage at 0 plus. This was 10K, 0 plus, right? 0 volt, t equal to 0, t equal to 20 millisecond, and this is 5 volt, right? And this is 1 microfarad, 1 microfarad. Okay, and this is what the V in is given, right? So the moment you see this kind of question and supply is also given, whenever the supplies are given, you have to be slightly cautious. Plus 12 volt and minus 12 volt, right? They are asking the voltage 0 plus at 0 plus watts LV. So this kind of questions are like, if you see the capacitance and the resistors, you will think that this is a differentiator circuit, right? But as you go, see, after t plus t equal to 0 plus, your op-amp will get saturated, right? Your op-amp will get saturated, or you can say, after t equal to 0 plus, your capacitor will continue to behave like a short circuit, right? After t equal to 0 plus, capacitor will continue to behave like short circuit, okay, as short circuit. So what will happen? This potential will be higher than this potential, right? So what will happen is that this overall circuit will behave like a comparator. Okay, comparator. So the answer for this question will be 0 plus equal to minus 12 volt, because the inverting terminal will be higher than the non-inverting terminal, right? So the answer will be minus 12. This question was asked for 2 marks, right? So you can expect question in the HAL examination of the from this, okay? Right. So let me take more problem from the GATE 2021 if they have been asked, right? Okay, so one of the very good problem they asked is the question from the clamper circuit, right? What was the question here is that an asymmetrical periodic pulse, an asymmetrical this is again GATE 2021 problem. An asymmetrical periodic pulse train, okay, pulse train V in of 10 volt amplitude with on time t on equal to 1, right, millisecond, and off time t off equal to 1 microsecond is applied, okay, is applied to the circuit shown in the figure, to the circuit shown in figure, okay, and the diode D1 is ideal, and diode which is connected here, right, diode D1 is ideal. So what you have to find here? By looking at the circuit, you will be able to identify that which circuit is this, right? Okay, so this is what the vein is, okay, this kind of a vein, right? This is 20 nano farad, okay, and there is a resistance which is 500k, and this is a diode, and we have to find the output across the diode here. I mean, the output is measured across the diode, okay. This is just a clue. If the output is measured, if output is measured across the diode, it means that this is a clamper circuit, right? Clamper circuit, okay, clamper circuit, okay. So in fact, you don't need to solve the question. What was the question then? What is the question then? This is just the information given to solve the question, right? And an asymmetrical periodic pulse of this amplitude on off, okay, t on is 1 millisecond, off time is this, okay, duty cycle you can compute from here, is applied to the circuit, okay. The diode D1 is ideal, they said, means diode can be replaced by open circuit or short circuit, no problem, okay. So the question they have asked is the difference between maxima and minima, okay, and the difference between maximum voltage, the difference between maximum voltage and minimum voltage of the output waveform, of the output waveform. Okay, V naught. So as I said in the study class that, clamper does not, okay, note, you have to keep this in mind always. Okay, clamper, see how I'm able to answer this question in 3 seconds, because we know that I'm able to identify the given circuit is a clamper circuit, right? Circuit does not alter the difference between maxima and minima of the input waveform, right? So whatever the difference between input waveform, maximum and minimum input waveform, right? That will be the answer, right? The same, okay? So you need to construct what kind of input they have given. See, the input waveform is a this kind of a waveform. Okay, so on time is what? On time is 1 millisecond, right? 1 millisecond is the on time, right? So it is 10 volt. You can see it is 10, right? Again, it is off for 1 microsecond, right? Like this. So what is the maxima here? 10. What is the minimum here? 0, right? So V max minus V min is equal to 10. So your answer for this question will be 10 only, right? Your answer for this question will be 10. Okay, this is the answer by this is by practical answer, right? So the VO max, VO, okay, VO max minus VO min will be 10. Okay, so what kind of clamper is this? See, the diode is pointing downward. It means that it will move your waveform downward, right? Your waveform is basically looking like this. Okay, now your waveform will be, this is input waveform, right? And the clamper waveform will be like this. Let me erase this, sorry. This is minus 10, this is 0. Okay, 0 and minus 10. So this was 0, okay, and this is 10. Of maximum and minimum, that is 10. And what is the difference here? That is 0 minus of minus 10, that is 10. So please keep this in mind. The difference between the maximum and minimum, peak to peak, is not changed, right? If there is a clamping circuit, right? If there is a clamping operation. Okay, this was very good question. This kind of question can be done within 3 seconds or 10 seconds, right, in the examinations. Okay. Right. Now, let us take one more problem, the op-amp problem, right? And also one thing you have to keep in mind, asymmetrical waveform. Here I have taken symmetry here, right? So what you can do here is, and there is a time, okay, just to explain you, okay, I have drawn like this, okay, but you have, if you draw this, this, right? So you have to draw asymmetrically, okay? You have to draw asymmetrically like this, okay? This kind of a waveform you can draw. But needless to focus on the shape of the waveform, because they are asking the answer based on amplitudes, right? So nothing to worry here, okay, regarding the waveforms and all, how to draw the waveforms just to get the answer correctly, right? So remember, peak to peak voltage will never get changed if you will pass your inputs waveform from the clamper circuit. And how you will be able to identify that is clamper circuit? If you are computing, the output waveform or output across, measure the output across the diode. Okay, so please first of all identify the circuit, right? This is very important, so you can minimize many steps. Op amp problem again in the year 2021, it was very good problem, right? So let me consider the circuit with an ideal op amp. Okay, consider circuit with an ideal op amp. Okay, shown in the figure. Okay, and you have to assume as well, assume that you have to assume here V in. V in is far less than VCC. Okay, and the Vref, one Vref is also given, is far less than VCC supply. It is obvious, right? The condition at which they have asked the question, the condition at which the V out equal to 0 is V out equals to 0, right? V out equal to 0. So as they have said that the V out is equal to 0, okay, V out equal to 0. Okay, so let me draw the circuit here, and already they have told you that the output is 0, right? So you don't have to worry about that. You have to find the output and equate to 0. So circuit is given here like this. So there is a V in, there is a resistance, again one resistance is there, and there is a Vref. Very good circuit, right? Connected to your V out, there is a VCC, right? So this is your V in, and this is your Vref, capital Vref. Okay, this is R again, and this is RF, this minus, this is plus, and this is VCC and minus VCC, right? And they have given some options, right? They have given some options as well. Your options are given as V in equal to 2 plus Vref, option B as V in equal to 2 times of Vref, option C equal to V in equal to Vref, okay, and option D equal to what? V in equal to 0.5 times Vref. Okay, so these are the 4 options given, and this is a question. So as far as we know that they have given 2, this is what the current source only, right? As we know, right? Already we know this is current source only, right? You can say. So okay, so this is what the inverting stage, right? Inverting amplifier. Okay, because this is grounded. From the virtual concept, we can say there is a 0 voltage here, right? So one at a time, you can consider one at a time, because you need to apply superposition, right? You need to apply superposition because there are 2 sources. We can say that by superposition, in one line you can answer this question, right? By superposition, if this diode is off, initially you can consider this diode is off, right? So this R will be also gone because this there is a 0. Okay. So what is the output here? Total output I'm writing, right? V out will be what? Because of this V in, what will be V out? Minus RF1R times V in, right? Minus RF1R times V in, remember. Okay. And one more situation is given. This is basically minus to plus. Remember this, Vref. Minus to plus, right? Now forget about this Veen, right? Now forget about this Veen. Okay, let me erase this. So this R will be gone. So now you can write V out. So it will be plus because there is a minus sign because of inverting amplifier, but the input is reverse now. You know, Vref is equal to what? Minus Vref is given here because minus plus. You can say this is plus RF upon R Vref. Okay. What you can do here is this is given as 0. So you can equate this, right? You can equate this. So as V out equal to 0, so minus RF by R V in plus RF by R V ref equal to 0. So guys, you can say that this and this get cancelled. So V in equal to V ref. In single line, you can solve this kind of question, right? If you are able to identify the circuit and you can apply superposition, right? Principle. So this kind of question can be done within 10 second or 20 second, right? If you are smart enough, and the op amp is ideal, op amp must be ideal, and this given op amp is ideal, right? So the answer for this question is C, V equal to V ref. Okay, so this kind of question was asked in GATE 2021. Okay, so we are trying to solve some previous year questions of GATE which can be asked in your HL examinations, right? This was very good question. One more question was asked in GATE from op amp only. That also I'm going to bring. And in next few classes, we will discuss problems only, BJT related problems and MOSFET related problems, right? And how we have to find the gain and all using some by inspection techniques, right? Not by following lengthy methods, right? What you know. So we will try to find the gain of any amplifier with the help of inspection techniques, like looking impedances from different terminals and taking the ratio of them. We will not go for a small signal model and then find out the gain, because that will consume a lot of time for you. Okay, right. So let me take that question. Yes. So write down the question here is that it is again asked in the GATE 2021. For the circuit with an ideal op amp, for the circuit with an ideal op amp, okay, shown in the figure. Shown in the figure, right? And the Vref is fixed. Vref is fixed, okay. So let me draw the circuit here and then we will see what question they have asked. This time they have given input in both the terminals, okay. So it is a combination of inverting and non-inverting both, right? So again, you can apply a superposition, right? Whenever many inputs are given, so always apply superposition, right? And the op amp is ideal, so you can go for virtual sort concept. This is given here. There is a resistance connected to it and there is a V out. Whether you draw load or not, it does not make any difference. 100 ohm RL. As I said that output is independent of this load, right? So there is a Vref again. Two question was there from op-amp in gate 2021. So you can see the importance of op-amp, and the op-amp is quite easy as solving op-amp. If you know the concept like this, I mean, if you know the problem solving technique like this, right? Plus 12 volt and minus 12 volt, plus 12 volt and minus 12 volt, right? And this is R1 and this is R2, right? So let me read out the problem first. Okay, what they have asked exactly. So this is 12. So if V out is equal to 1, they have asked that if V out equal to 1, if V out equal to 1, right? If V out equal to 1 for, they have given some V in equal to 0.1 and V out equal to 6. Again, they have given V in equal to 1, right? When V out equal to 1, for V in equal to this, V out equal to 6, when V in equal to 1, where V out is measured. See, this much information is given, so you don't have to get scared, okay, because the problem is quite lengthy, you know. The problem is not lengthy if you know the concept like this, you know. If you are able to apply the superposition and you can write the output of the op-amp in one line, and just you have to plug these given information right in that those equations where V out is measured across RL, right? RL connected, RL connected at the output, okay, at the output of this op-amp, the value of, they have asked the value of, you know, ratio of RF and RIN, they have asked, right? RF upon RIN. This was the question, very good question, right? And the option they have given is 3.285. This is 2, right? Option B they have given is 3.825. Option C they have given is 5.555. And option D they have given is 2.860. Right? So it is easy question again. Let me get back to the circuit. Forget about given information, right, for the time being, and try to compute output. Okay. So as we know that if we forget about this Vref, right, so we can find the output with respect to this, and you have to find the total output, right? You have to find the total output. Okay. So you can write here. Okay. So when this guy is working, right, this guy is not working, so output will be what? Okay, when Vref is not, yes, first, okay, for V in, right, Vref is short circuited, you can say, or removed. So your output will be what? Output will be minus RF upon R in. Okay, let me go back to the circuit. RF upon R in times V in, right? And second case is what? When Wheel is not working, right? So then what will happen? Okay, so in that case, when this guy is not working, suppose, When this guy is not working, this is working. So the answer will be Vref times, here you have to find the potential here, right? So Vref R2 by R1, you can consider that is beta. Okay. So here you will get plus as 1 plus Rf upon Rin times Vref, okay, times R2 by R2 plus R1. Whenever this kind of questions are asked and the expression is becoming big, okay, so what you can do here is you can just multiply this inside, okay, and so just let me multiply this. V out equal to minus Rf upon Rin V in, right, plus Vref. You can consider this is just beta, you can say. So Rf beta plus Rf upon Rin, Rf upon Rin Vref times beta. Okay. So now what you can do here is you can plug informations given. You can plug this value V out V in equal to 1, V out V in equal to 0.1, right? So these values, if you will plug and subtract them, okay, if you will subtract both of them, okay, if you will subtract both of them, so you will get two equations and two unknowns, right? Two equations, right? So the equation you will get here is first equation. What you will get? So this will be cancelled off, okay, if you will subtract. So this will be cancelled off, remember, right? So let me put two equations and two unknown, right? So we can consider this is basically x, right? Okay, so let me now put the okay, so V out equal to 1 for V in equal to 0.1. So 1 equal to Rf upon Rin, which is has to be R, and 0.1 here, plus x, you can say. And second equation you will get here is 6 equal to minus Rf by Rin into 1 plus x. Now you can subtract the two, right? So the equation number 1, this is equation number 1, this is equation number 2. So this will get cancelled, right? And they will be what? So you can see here, you can subtract, right? So let me subtract here. So let me write 1 and 6 here. 1 and 6, that is Rf by Rin, 0.1 already cancelled, right? Plus x and minus Rf by Rin, that is 1 plus x. So let me subtract. So minus plus minus, so this will get cancelled, okay, and here you are getting minus 5 equal to this is minus and this is plus, right? So you will get 0.9 Rf by Rin, right? So what you are getting here is that this is 0.9, okay, because you are 1 minus 0.1, right? So that is 0.9 only, okay, 0.9. So Rf you will be getting here is like Rf upon Rin is equal to 5 upon 0.9 minus, right? So you can divide and you will get what? Minus 5.555 kind of a value, right? This was very easy question, right? Again, so always don't get disturbed with these terms, right? If they are unknown, you can consider, you can club with certain constant or variable, whatever you want, and cancel them, right? So this was the question, very easy question asked in the GATE examination, right? In the GATE 2021. Now we in the next class, what I'm supposed to discuss is the bipolar junction transistor and the MOSFET. Okay, and we will also cover important topics like oscillator. Okay, plus Smith trigger, few problems, right? Smith triggers, multi vibrators, right? Because the question can be expected from here as well, right? Multi vibrator and some filter problems, right? Filter problems and uh, frequency counterpart of the counterpart of each circuit, right? Like frequency response of op amp, frequency response of diode, frequency high, how does your diode behave in high frequencies, right? All those things. So we will discuss, frequency response of and problems. Mainly now in our classes, the problems will be solved more. Okay. So for today, thank you so much. Okay, so keep practicing and keep learning, and let us know uh, if you face any problem in analog circuit. Okay, by the time you will not face any problem if you will watch these lectures carefully. Okay, thank you so much. We'll catch up in the next class.